We're going to look at the general cases. So in general, using algebra, that's usually what we're talking about when we refer to general. So for any numbers, what happens with, so general, oops, I shouldn't have the word with there, it's not even making sense. So general operations, so in terms of algebra, the operations with complex numbers. So in other words, what does it look like when we add, subtract, multiply, or divide any group of complex numbers? Well, we'll start with addition and subtraction, and we'll see they're very similar. So if I take a complex number, we're going to have that written as a plus bi. A is being the real part of the number, bi is the imaginary part. But let's say we take that and we add it to some other complex number, c plus di. So two complex numbers being added. Well, in addition, we're going to add like parts. So this really becomes a plus c, or our two real numbers, and then plus bi plus di. You might want to think of this as a plus c plus I is the common factor. So you can think of this as I times b plus d, or a plus c plus b plus d times I. And that just means that if you're adding up two complex numbers, you add the two real parts, and then you add the two coefficients here, the b and the d, and leave the I. So for example, if we had 2 plus 3i plus 7 plus 6i, that would just be 9 plus, well, 3 plus 6 is another 9, 9i. And that's what we're saying right here. Subtraction, almost identical. Except now the idea is we're subtracting. So if you have a plus bi minus c plus di, what do? Well, we subtract the like parts instead of add them. So we have a minus c, and then we have to remember to add in the bi minus di. So bi minus di, what is that? Well, just like before, we can think of I as the common factor, a minus c plus I times b minus d, or b minus di plus a minus c. I think the one confusing part here might be, well, why are we adding this? Well, we're subtracting a minus c, and then, that might help you think of it, and then we're subtracting di from bi. So, and then implies addition, and that's exactly what's happening here. So if we had, for example, 5 plus 2i minus 6 plus 8i, our formula here tells us you do 5 minus 6 to get negative 1, and then 2 minus 8 to get minus 6i. And you could think of that as negative 1 minus 6i, or negative 1 plus a negative 6i, which is kind of how we wrote it here. Multiplication we can also represent in a general case. So for multiplication, we can think of one complex number, a plus bi, times another complex number, c plus di. Well, when we're multiplying these out, we're just using the distributive property. So a times c, that equals ac. A times di equals ADI, and we're adding these parts up. And then we have the other term, BI times C is CBI, and then BI times DI is plus B, well, D times B times I squared. We can simplify this a little bit. Here we have AC plus ADI plus CBI minus DB. Because I squared is just equal to negative 1, negative 1 times dB is minus dB. So instead of adding a negative dB, we could just subtract dB. And we can actually go a little bit further. A common factor here is I in both cases. So we can think of this as AC plus AD plus CBI. We factored that I out. Minus dB. So we can actually go a little bit further with this as well, or we can think of this in a different way by combining like terms. We still have AC minus DB plus AD plus CB times I. And that looks pretty awful, but basically what it's saying is if you take one imaginary number, one complex number times another complex number, look what you get. You still are getting a complex number, where the first part is a real, right? Real numbers subtracted by real numbers will keep you in that group. It won't. The only way to get out of the real numbers, that I can tell so far at least, is to take the square root of a negative. And then over here we have an imaginary part. It's important to realize that it doesn't matter what two complex numbers are multiplying, we're still going to get another complex number. And last but not least, we have division. And division actually is surely, as it was before, the nastiest of all. It's going to be the hardest to show in general. But it's important to look at because we'll see the effect of the conjugate. So we'll look at division and the conjugate. So we'll set up one complex number divided by another. We'll keep the format, and we write division up here so we don't lose track. So A plus BI, one complex number, divided by C plus DI. Well, to eliminate this imaginary number here, we multiply by the conjugate. Real number is the same, imaginary part's the opposite. Do both the same to the numerator and denominator. And then we're going to evaluate that over here. Up top we have A times C, which is AC, and then A times minus DI, which is minus ADI, and then BI times C, which equals positive BCI, and then BI times minus DI, which is minus BDI squared. In the denominator, it's going to look a little bit prettier. C times C is C squared. And then C times minus DI is minus CDI. And then DI times C, we're multiplying the other term, is positive CDI. And that's nice because we have two opposites here. And then DI times minus DI is minus D squared I squared. Okay, so we're going to simplify. We're going to remember that I squared is equal to negative 1, the square root of negative 1 times the square root of negative 1, which is just negative 1. So wherever we see an I squared, we're going to replace that with negative 1, and wherever we see like terms, we'll combine those as well. So we have AC minus ADI plus BCI plus BD. What I did there was I subtracted a negative BD, because it's negative 1 times BD. Subtracting a negative BD is the same thing as adding BD. In the denominator, we have C squared, and this is where it looks a little bit prettier. We have negative CDI plus CDI. I have no idea what those are, but if they're opposites, they add to 0. And then minus D squared I squared. Well, I squared is negative 1. And as the same principle before, we're going to switch the sign to plus D squared, because negative 1 equals I squared. Negative 1 times negative D squared is plus D squared. And, of course, we can go a little bit further. I can still combine AC and BD. So we have AC plus BD, and then minus, I is a common factor in these two terms, so minus AD plus BC times I. But actually I want to change the sign here. When you're messing around with these equations, just make sure you keep the sign straight. This should be a minus BC because it's positive BC here. So if we're saying you subtract AD and then subtract a subtracting BC, so add BC. So you want to be able to distribute this negative sign into the equation. And in the denominator we have C squared plus D squared. And we can go a little bit further than this. We can think of this as AC plus BD, and we're almost there, over C squared plus D squared. Right? I'm saying that this term minus this term times I It's going to be the same thing as this term over c squared plus d squared minus the other term, AD minus BCI over c squared plus d squared. And one important thing that jumps out at me is that, look, we divided, and no matter what we did, we were able to get another complex number. So dividing by complex numbers won't get us out of the complex group. Right? We're still going to end up with a complex number. And although we're not really going to memorize this, of course, it's important to realize that in our denominator, we're always going to have c squared plus d squared. That might help us out a little bit. So if you had these two numbers, you could just look at right away c and d. And whatever our answer is, it will have c squared plus d squared in the denominator. And actually, I made a mistake over here. This should be d squared, right? And that's the general cases.